Okay, C2, mathematical induction and sequence. It looks like mathematics class, but most of mathematics, I told you most of mathematical tools has been developed by physicists to solve the physics problem, and it can also be applied to many kind of fields in any science and economics and so on. So the, the very simple but fundamental sequence that Galileo Galilei has found is the trajectory of a falling body. He thought the basic idea of Aristotle, and people thought that a feather falls down slowly, more slowly than a stone. Everybody knows. So, however, they generalized that simple result to everything, including celestial bodies. So that was a great mistake. And that wrong belief has been believed for a long time, more than 1,000 years. And all of a sudden, Galileo Galilei produced introduced this new idea, but the fact based on experiment. Science is not simply a conjecture or inspection, but it must be based on the experiment. So I say, and many scientists say, the first scientist and the first science is the physics, and the first scientist is not Aristotle, but Galileo Galilei. He introduced the frame of reference from which we describe nature. And then, more specifically or quantitatively, Descartes introduced explicit frame of reference that is called the Cartesian coordinate system, whose three axes are perpendicular to the others. From then on, mathematics has been developed in an algebraic way. Well, with algebra, we could describe the geometry. So this is a great triumph of physicists to change the world and change the view on looking at nature. G here is called constant gravitational field, the gravitational acceleration. So it is not an exact constant that depends on the position on the surface of the earth or height and so on, or depends on something buried inside the earth. And more or less, the number is approximately 9.8 meter per second square. This is an acceleration as time as a 1 second pass, then we have 9.8 meter per second increase in the velocity of a freely falling body if we neglect the air friction. Let's think about from the definition of the change in the velocity per change in time interval. Change in the velocity, we can multiply this equation by delta t. And delta t on the right-hand side in the denominator cancels. I can find delta v. And that is g times delta t. Okay? And here delta v is the change in velocity from time t to time t plus delta t. Because g is a constant in here, If I introduce delta t in a uniform way, so I can change the velocity with exactly the same amount repeatedly. In that case, I can introduce a simple sequence from n runs from 0 to n over any integer. Sure, if something is falling, starts to fall, then at some point it will hit the ground. It will hit the ground. So after that, we cannot apply this formula, but we assume that this falling body doesn't hit anything during the time interval we are interested in. Okay, so we can introduce a number line representing time, and there should be a shift from 0 to this one is assumed to be delta t, and 2 delta t, and so on. So actually this is dimensionless number, so I must multiply delta t here, 2 delta t, and so on. So I can define a sequence. A function depends on this argument that is an integer. And we define Vn to be the velocity at time Tn. Okay. In addition, why don't we introduce another sequence that represents a position of the same particle? The question is that find the velocity and the position at time t equals Tn. Okay. We call this kind of here. This sequence Tn is arithmetic sequence. Let's see. Vn plus 1 minus Vn is defined to be delta Vn. Okay, in that case, this is a constant as long as we choose delta t the same for any n. So the shift in velocity is uniform. We can introduce summation formula for this arithmetic sequence. Okay, right now, the last term, and it began with a 0 to 1 and 1 to 2 and so on. We find the same term appears with the opposite sign. Vn minus 2, we have positive sign. So they cancel. At the end of the day, we only have the last term and the first term. And the right-hand side, they are all the same. How many are there? We have started n equals 1 and with n. So we have n equations. Therefore, the sum of the right-hand sides, g delta t times n. Sum of the left-hand sides is a Vn subtracted by V0. All right. So n delta t, what's that? We have defined this one, the simple thing, from T0 to Tn. We have a n gap of delta t's. As a result, at plus V0 on both sides, we arrive at this formula. This is what you learned in high school process, finding out the general solution for the arithmetic sequence. In a similar manner, I can repeat the same job in here. However, this velocity, they are all different. But that's fine. Let us try. As far as the left-hand side structure is concerned, the difference of V's has the same structure as the differences of X. So if I add all the changes in the position, the intermediate values will all cancel. We end up with the final value subtracted by the initial value. We usually say this is the displacement. Displacement, change in position, is called the displacement. So this means that it has been changed from 0 to n. By the way, in a previous case, to compute the change in velocity, the right-hand side calculation was so trivial. So I just add the same object, g delta t, by n times. It is simple multiplication. And multiplication of by n to delta t results in the change in time. However, in here, even though I have a common factor delta t in here, after I factorize the right-hand side sum, I have another sum of a series. The sum of series is called, sum of sequence is called series. So from 0 to n minus 1, there are n terms. I have added the vk's from, or where k runs from 0 to n minus 1. So 1 to n, there are n terms. Subtract all these by 1, the 0 to n minus 1. Still, they are n terms. Okay. And I have a common factor, delta t, this. So I believe everybody knows about the summation symbol. Later, we will see that the integral, this comes from Leibniz. Leibniz introduced this one. And after that, Euler studied the integration a lot. And after the classical mechanics was established by Newton and Leibniz, Euler applied that idea to rigid body system that, for example, the spinning top or something like that, collective objects, motion. So in that calculation, it was very useful to introduce this kind of summation notation. Don't forget, all these important mathematical symbols are not invented by mathematicians, but invented by physicists. Anyway, move this initial value to the right-hand side. What we find is the position of a particle at t equals to tn, it can be expressed as a sum of the initial position and sum of displacements. You know, v1 delta t, v2 delta t, v0 delta t, and so on. These are small displacements, and the sum of everything will result in the total change in position. So what we want to do is decrease this delta t arbitrarily small and find out whether this computation reaches an accurate value, as accurate as possible, if we change the accuracy of the measurement of time. So finally, we will reach the point that simple sum approaches a constant value that is called integral. Okay, let's return to the arithmetic sequence. To simplify everything, we we repeat what we learned in high school. Any arithmetic sequence, consecutive elements, subtraction, difference is uniform. So this is called the common difference. Using sigma notation for the summation of a sequence, summation of sequence is called series S. I use the partial sum. Partial sum means I sum this sequence by a finite number of elements. If I increase the n goes to infinity, it will be the total sum. Okay, in here, I can substitute the general term for this sequence represented by this common difference arithmetic sequence. We know, everybody knows that if I substitute k equals 1, I can obtain the initial term. And if I substitute k equals n, then it becomes from 1 to 2. What's that? 2 minus 1 equals 1. Okay, when k equals 2, 2 minus 1, 2 minus 1 is k minus 1. So this is the shift from the initial value. Okay, let us simplify this calculation. This d and a1 are constant, so this we can expand everything and find out that the summation can be divided into two pieces, sum of ones and sum of k's. And perhaps you know, some of you know, or some of you might don't know, but you can do it by yourself to find out this sum of k is 1/2 n plus 1. Using this manner, we can reorganize this computation. Finally, we will reach the point. This is when I add all of the terms in the arithmetic sequence, reorder the opposite order. This changes by d, by plus d, plus d, plus d. And from n to 1, it changes by minus d, minus d, minus d. So plus minus, it cancel. So this sum and this sum, every partial sum should be the same. And we have n pairs. So that's the reason why we have double series. So I divide n by 2, multiply by the first and the last term, sum of the first and last term. This is a usual way to find out the series, partial sum of a sequence. Perhaps somebody do not know how to compute this. I have introduced how to compute this. You can follow this calculation. But as I have written as a title of this lecture, we are interested in generalize some result that we have obtained from a finite trial. I mean, for any integer n, can it be the same as this? That is our problem. So we use mathematical induction to generalize our finding to be applied to any integer. First of all, we have seen k to the 0 is just 1. Add 1 by n times, we know that it is n. And k to the first power, the result is, forget about the intermediate result, just answer is, oh, it seems to be 1 n squared something. So if I increase n, this term can be neglected in comparison with the leading contribution. Oh, should there be some general rule for the sum of k to the alpha power, something like that? That is our question. I would like to make an educated guess from our previous result that sigma 1 equals n and sigma k equals approximately n squared over 2. There's something that approaches 1. So I'm interested in finding out what it is. Okay, first of all, we have experienced that the sum of 1 ends up with n, power n. Aha, k, this one has n squared. So k squared, the answer, some of you may know there's a n plus 1, 2n plus 1. Somebody has memorized this, but actually it is a proportional to nq, and we will find that it is just a one third of n cubed, something like that. And if I neglect the remaining piece, that approaches 1. Okay, so we can construct from this our guess, we might find a term that has a subleading power. That means the maximum power is k to the 1, then the maximum power should be n squared, and perhaps there is a subleading powers or constant, something like that. Using this assumption, we can construct some undetermined parameters that should be a constant. They should be constants, but we do not know very well. Using this way, we can introduce some simultaneous equation. How? Actually, we know some specific values for sigma 1 and sigma k, so they are constraints. Just to substitute them and repeat this one with the explicit number, n equals 3 and 4 and so on. And actually we will find this equation, even though it is a very tedious, even middle school students can solve this problem. How? It looks complicated, but 2 by 2, 2 by 2, you can solve it in a straightforward manner. If you're diligent, or if you're clever, or if you have some skill using computational coding skill, then you can solve it. What I want from you is not find out the exact solution out of it, but just find out the way how to generalize our experience to guess, to predict something that has never been tested yet. So using this solution, I can find, without applying the method, what we learned in high school, we can reproduce the result. I'd like to know this formula, if this formula is really generally true or not. That can be found by applying mathematical induction. Mathematical induction is used for the function of integers. Okay? Mathematical induction is basically used to define the integer, set of integers. Using that method, arbitrary function of integer, that is a sequence, general term of a sequence, can be found. So Here, I have made an educated guess by making use of the result by substituting this stupid way, brutal force way of substituting all of the numbers based on a postulate that they are all expressed in a power series, this finite polynomial of n's. That is the only assumption that I have made. But let's see if this guess is really true or not. That is mathematical induction. For initial value until n equals 1, 2, 3, 4, it worked very fine. I'm interested in the fact that if it is really working for n plus 1, let's see. Sum until n plus 1 can be found by substituting n plus 1 for the previous n. So substitute n plus 1, in here n plus 1, and here n plus 1, something like that. Then I get the sum result. That is this. And actually, I can repeat this one, I can make use of this one and add one single term after that. That is this. Previous sum until the end is nth term, and then I add one more term that is n plus 1 squared. We have found that these two values are the same. That means for any n, it is satisfied, and it is true for n plus 1. Therefore, give me any arbitrary integer, then I can check it is true for any integer. That is the application of mathematical induction. Okay. Let's see. You can read it through to reproduce the result for k to the q. Simple application, straightforward way. Next, we are interested in extending this previous result to find out the continuum limit. What I mean is we have found some time dependence of position and time dependence of position from changing velocity. Velocity changes by the same amount as time passes by. What happens if I decrease this delta t arbitrarily small? Right now, we have some empty space that is the numerical error that we might make. But if we slice this one, these histograms, as narrowly as possible, then the sum of the histograms will approach the area under this curve. And actually, this is a straight line, and we know elementary school students may know the area of a trapezoid is height sum of two bases multiplied by 2 at 1/2. Okay, this is h, a, b, something like that. So we know the exact answer in this case. So using this method and our general terms for the summation of k's, arithmetic series, we'd like to find out the area using this summation with the limit as this n goes to infinity. N means number of bins goes to infinity. We'd like to introduce a simple function. This is x, and this is f of x, and we'd like to measure the area. Okay. Then it is good to introduce the arithmetic sequence that divides the interval of x that starts from in here a to b, a to b. Slice them into n pieces. That means this difference b minus a is divided by n, and this sequence x0 through xn can be reproduced by this simple arithmetic sequence. You will find this is x of n, and this is the width. This is small, tiny width. We have divided this width by n. So this is a width, height. So some of this represents the area. But we do not know whether these errors accumulate to make a finite error or not. The mathematician has found that this value this is integral. That means integral means the actual area, and there was a trick, actual area, and we can measure the area using this red histograms or this blue histograms. So blue histograms overshoots greater than this actual area, and red histograms undershoots. So its area, this red one is smaller than the actual area, and blue one is greater than the actual area. However, in the limit as n goes to infinity, if we apply what we have found to this inequality, our final answer is they are squeezed. It is tedious calculation, but it is finally proved to be trivial, and all of the results are squeezed to a single value. This is, in mathematical sense, this is called Riemann sum. And this is upper sum and lower sum, overshooted result and undershooted result. If they approach the same value, we call this integral in a mathematical sense. But elementary school students know already that the area, what is the area of the trapezoid? And they would say, without this complicated result, they will give you the answer. Okay. This is very useful in our future calculation. However, detailed derivation, somebody might be interested in, so everything is written in a correct manner, so the advanced student can repeat the calculation. But if you're not familiar with it in detail, forget about the detailed following of the explicit computation. You can always refer to these results. That's it for today.